So as it was said, I will talk about different architectures. So unfortunately, so I'm a bit cheating here. There will be no results on FPGA, but at least I hope I will give you an idea of what it is, and how it works. Okay, so the outline is the following. So I will have a few words about Metalwalls as an application. What does it do? Then the effort we did with Abel, so my colleague, so a postdoc that we have at Maison de la Simulation, to optimize and port it on different architectures. So our different architecture here, I mean Xeon, Xeon Phi, and GPUs. And the rest of the talk will be dedicated to FPGA to give you the idea behind this kind of technology that might emerge in HPC. Okay, so Metalwalls is about molecular dynamics. Okay, so that's initially a code developed in England here in Oxford, and now maintained by Mathieu Salan at UPMC. The original version was written in Fortran 90 and pure MPI application, and so there are a lot of different codes around in doing molecular dynamics. What's the point of having yet another one? So this one does few things, but very well. So typically, they can make simulation of electrodes with constant potential. That's something that is quite complicated and that this code does quite well. So that's typically the kind of system that is simulated. So you have two electrodes here in carbon. So that's the gray thing you see here. And all the bubbles here are atoms. So that's ionic liquid. And the idea is to apply a difference of potential between the two electrodes and to see how the liquid reacts on it and the kind of structure that appears in the material so near the electrodes, because that's the kind of thing that is very difficult to measure experimentally. And so it's to help experimentalists understand their measures. And this device, at the end of the day, is to store energy, because you apply you can put some energy in the system, you unplug, and then when you plug it again, the supercapacitor can give the energy back. Right. Well, what's wrong with all the equations? Okay. Anyway. So that's with latex, so I don't understand what's wrong here. Yeah, so that's the particularities of Metalwalls. That's to be able to simulate constant potential electrodes, and yes, and then the idea is to minimize the energy. So once you have a set of atoms in the bulk that are in certain positions, is okay, where are the charges on the electrode so that the total energy of the system is minimum. Okay, so then from an algorithmic point of view, so basically the code is around 20,000 lines of code, so that's not that big for a production code. And among these 20,000, only 7,000 are really doing intensive computations. So that's pretty small. That's why I took the opportunity to use this code as a test bed to test different architectures and to try to compare how the architectures behaves with this type of codes. So you have an initialization step, and then you have shake algorithm that move the molecule. And then once you have your liquid that is in a specific position, then you try to find the location of the charges on the electrode. So that's this minimization process I just talked about, so with a conjugate gradient. So once you have the charge on the electrodes, then you can calculate the forces that applies on the liquid, and then you can push the atoms of the liquid, and then again form back the molecules that are in the liquid. Okay. Only the green boxes are parallel, so meaning 99.3% of the execution time in serial. So it means that with a couple of hundreds of cores, we are limited by Amdahl's law. But then that's part of the to-do list to parallelize the blue box as well. All right, so what did we do? So a very strange thing. I don't know, because that's okay. Anyhow, so we did several stuff on the code in order to improve the performance. So typically, we did some memory footprint reduction. So instead of computing some quantities once, storing them, and accessing them several times, the idea was to not store them, so then to reduce the memory used, but then to recompute on the fly this kind of data several times. And as computation nowadays, at least in the current architecture, costs much less than moving data from memory, then you, in the end, that improved the performance. Then we worked on vectorization. We implemented some cache blocking techniques. So that's typically when we went to KNL, so Knight's Landing architecture. We've seen that so not having an L3 cache was really killing the performance. And that's where we detect that some cache blocking techniques were needed here. And then we used OpenACC to port the code on GPU system, and I will show you some results afterwards. So one thing that is important is that at the end of the day, we still have a single code base. Okay, we don't have 3 codes, one for GPU, one for CPU, and one for KNL. It's still one code base, so full of pragmas because we have OpenMP and OpenACC pragmas. But still, it's one code base, and porting to KNL brought something on cache blocking that is also relevant on CPU. And porting to GPU also improved the performance because OpenACC was more strict in some areas, so we have to change the code. And back on CPU, it was also faster. So doing this exercise of porting to several architectures improved the overall performance of the code on all of them. So that's interesting point to note here. And then if you look at the savings, that's quite important, at least from my engineer perspective. So this code has been granted 28 million of CPU hours in 2016. And without the optimization we've done, the code would have required 70,000 million CPU hours to do the same experiments. So that's huge saving here, I would say. So yeah, improving the code makes you can do more science with the same amount of CPU time. Okay, now, so as I said, so as the code is pretty small, we could try to compare architecture. And so the idea is to, okay, I want to simulate one system, so a certain amount of picosecond of this simulation of one system, and I want to run this on different architecture. And I want to compare 2 things. So the performance, so how many picosecond I'm able to simulate per unit of runtime. Okay, so that's what I call performance here. So higher here is better. And also the energy, because as we all know, the energy requirement for supercomputing system is more and more a challenge to have more computing power in the same on the same supercomputer. So then here I measure also the energy to solution. So how many joule were required to achieve the simulation. So here on this axis, lower is better. So how ideal scalability looks like on this kind of plot. So typically you have running on n resources here. So you need p watts, okay? And you need t seconds to execute the run. And you need E kilojoule that are required to fire up the machine. Now, if you double the amount of resources, so you're using 2p watts, if we assume a perfect scalability of the application, then the runtime will be halved. Okay, so you will have t over 2 seconds for execution time. And then the energy required, so it's 2p watt, but only half the time. So energy should be then stay constant if the machine scales also perfectly in energy. So a perfect scaling is simply a straight line on this kind of plot, and as neither application nor computer are perfect, then you will have a derivation. So here, on the right. So now, we've run the implementation on 3 systems. So Kernel, Broadwell, and Open Power System. And here is the results for intra-node. So okay, so as I said, normally the curve should go to the right. Here are going to the left. So we have an incredible super linearity of behavior, but not at all. It just means that the baseline is really awful, meaning that the energy you need so the green is the KNL, so the energy you need to run on one core of so you have a machine with node with a KNL, so you need almost as much energy if you are using one core or 64. Basically, that's what it means. So here, what you see in the energy gain is basically the performance. So you run a much smaller time, okay? But you do have an improvement. So then in performance, as you are increasing the number of core you're using on the system, then the performance is increasing. And same way on the different on GPUs. So it's not linear, but still interesting scalability. Unfortunately, on the Broadwell system, energy measurements were basically wrong. That's why you have a huge error bar there. So okay, so basically, we do not have a super linear energy scalability. It's just that using only, so letting just resources idle is not a good way to save energy. As soon as you have one node that is reserved for your computation, you will burn the same amount of energy, whatever you are using only one core or the full chip on this node. That's the bottom line of that's the morality of this this plot. Now looking at inter-node, so now if you're using full node but then several of them, how does it behave? So again, sorry, Broadwell energy measurements are wrong. Still, the performance is okay. And then I made the experiment up to the maximum of efficiency. Okay, as soon as efficiency is below 75%, I stopped. So that's happens at 5 nodes on KNL, 11 nodes on Broadwell, and yes, above 1 node on Open Power, then efficiency drops below 75%. So what do we see here? Is that's so top left is the best. So top left is here GPU. GPU is giving the best restitution time. So the best performance are still obtained with Broadwell, but I guess with a lot of energy. So I think it's much more on the right. But still, so with a good scalability, Broadwell has a better performance. But then if you And from energy point of view, so when the GPU is giving here the best results. Okay, but that's the sum up. So Broadwell is still the fastest. And at scalability limit, then so Kernel and GPU are 62 and 84% of this amount of performance. And from energy point of view, so unfortunately I don't have the Broadwell figure, but Kernel requires 2.5 more energy than GPU to get the same scientific results. Basically, that's it. Okay, and now if we look a bit into the future, so we know already that the energy budget for a data center that will host a supercomputer is fixed around 20 megawatts. So that's something that's kind of hard limit. The number of transistors per chip will be still increasing, but will be soon also be fixed due to Moore's law that will likely saturate in the coming years. So for me, relevant question is, so before we have quantum computing, I think silicon will still stay there for a while. But then how do you organize the transistor within a chip? So what kind of architecture? And I think we will have new kind of architecture that will emerge because this kind of thing saturates now. So, and then the next question is, how do you program this new chip? And how do you build so environments such that large communities are able to access them? So I think FPGA is still very exotic today. So for now, the current usage of FPGA, for example, is in the little boxes we have under our TVs to decode the videos that are coming compressed on the internet. So it flies in the chip, and then the chip implements the decompression algorithm in hardware inside the FPGA, and then you have the decompressed flux that goes out of the chip and then goes to your TV. So why not using this device to do scientific computation? So instead of having a decompression algorithm, then you have a molecular dynamic algorithm. So so this company, Maxeler, has this idea to propose computing system based on FPGA. So now it's 10 years ago they started. And they have computing solution with a software environment to program these FPGAs. And so I had the opportunity to try and to play with. So unfortunately, so it's still work in progress. I don't have any numbers now in terms of runtime and energy, unfortunately. But still, I can show you the spirit and how does it work, because it's very, very different. So if we compare the different kind of chip we are at our disposal for doing computation, so we have something that you know, most of you, so Skylake, so Knight's Landing, so it's still Intel chip, NVIDIA Pascal, and then you have this new guy, this Xilinx with a strange number, is a FPGA, okay? So they are all at the same kind of silicon technologies, running at very different frequency. As you can see, the FPGA is running much lower frequency, and then you can see the correlation with the power requirement. FPGA requires much less energy to run. Okay. So number of core. Then I put some cache. So it's not really cache, but okay. You have memory on chip. You can have fast memory. And then the peak performance is just indication, because peak performance doesn't mean that much on FPGA. One note here that peak performance on these three architectures are a bit theoretical. You have very few chance to reach these kind of numbers with a real application, whereas here you have a chance to get this for real. Okay, I will show you. I hope I can explain you. Okay, that's one of the, if you have one slide to remember on what an FPGA is this one. So let's start back with something that you know about processors. When you program, when you have a program that will run on a processor, at the end of the day, you have a sequence of instructions that will be executed. Okay, executed here. And hopefully you have, so you have vector processing units that will execute, so multiply and additions. But then a lot of space on the silicon is spent to have memories, so caches here on processors. And the big difference with FPGA is that here all the data movements are done automatically in hardware. So at some point you have an instruction that says, okay, load this address in this register, okay, and this address in memory, so the memory is even not represented here. And then depending on where the data is, so if it's in memory, is it in this part of the cache or this part of the cache, you have some automatic processes that will bring the data into this register. And depending on where it's sitting, so then the time spent is different, okay? And that's all the kind of job we are doing. So we guys, HPC experts, are trying to reorder this sequence of instructions such that when the instruction of loading a data appears, there is a large chance that it's close to the vector processing unit. Okay, so here in the processor, data movement are triggered by instructions. And what you program is the flow of instruction. FPGA is not a processor. FPGA is, so I will discuss a bit the different bricks. What you program is how data are moving inside the chip. Okay? So you have different elements. So you have BRAM. So you can think of it as kind of cache. So it's more local memory, okay? That you can pull some data from memory and then put it on the chip in some specific very fast memory. DSP stands for digital signal processing. So here you can do whatever fancy operation you want on numbers on any fancy number representation. So floating point, fixed point, integer representation of numbers on various number of bits, whatever you want, okay? Then you have, so LUT stands for lookup table. It's basically logic. So you have NAND, NOR, you have really logic circuits. And flip-flop, so that's tiny circuits that can store 1 bit, 0 or 1, okay? And then you can, and by combining LUT and flip-flop, you can rebuild those ones. But instead of having only LUT and flip-flop, then you have hardwire, BRAM, and DSP such that it's faster, okay? And what you program is how all these elements are connected. So you have your data that flow in here. They will be stored in memory. Then you will make a first addition here. And so they will have some logic. They will be stored here and so on. And so you have a path. That's what you program when you program FPGA. I will show you an example afterwards. But first, what's the kind of computing system that Maxeler is proposing? So the idea is to have one FPGA connected to some RAM on one card, accelerating card, so that what they call data flow engine, DFE, okay? And this one is connected with PCI Express, okay? Then you pack 8 of these cards in one box. So that will be one accelerator node, okay? So DFEs are connected either by PCI Express, but they have also an optical ring bus that is much faster to connect connection between the different boards. And these accelerator nodes are connected by InfiniBand, okay? So normal, some standard high-performance network in HPC. And then you set up a cluster, which is quite standard here. So with some normal CPUs that will be able to offload some part of the computation on these accelerator nodes. That's how it works. And so how do you develop? So that's one very nice thing about FPGA is that at each clock tick, you know exactly what's happening in the chip, where are all the piece of data are, and how it will flow to the next step. Okay, so just with a spreadsheet, you can build a performance model, and you know between 5 and 10% how fast, how much time it will take. So that's pretty magic compared to programming on processors. You have no chance with a spreadsheet to get everything. So the thing is that you play around a lot with LibreOffice or Excel to design. Okay, what will I do first? How I can show you an example afterwards if you want. Before implementing it, okay, and then implementation is only just doing. The second point is then, okay, once you have your design, you have to write the kernels, okay, and for this they have built a language, so they call it MaxJ. So that's a embedded DSL, so it's based on Java. So you are writing Java code typically. So, but specific to, you have kernels, and then you have some classes and some objects you can use, and everything then is then transformed into VHDL, and then this VHDL is transformed into the binary you will load into the FPGA. Okay, so they have all the software chain down to the hardware. So they have a Eclipse plugin, so that helps you to develop this kind of thing. And then the kernel you generate, then you can call them from C, C++, or Fortran. Okay, in that offload mechanism. However, to make a compilation, it's between 24 and 48 hours. Yeah, I won't go into the detail, but to go from the Java to the binary stream you will load on the FPGA, it takes between 1 and 2 days. So there is no way you wait for the compiler to just test something, okay? So the trial error with your Fortran code, so you compile, you run, you say, oh no, yeah, I forgot +1 here. Why is it so long? Complicated. The thing is that for now, there are very few users, okay, and they are doing one program, and they will use this program millions of times in millions of chips that will go in your box, TV box, okay? We are weird guys doing software all the time. So they are not, so all the tools are not ready for that. And the second thing is that we are also crazy because we want to fill the chip. We want to use all the chip, and then the software has to route everything and try to pack things. And that's so the routing algorithm is quite complex and hard to parallelize, I guess. And that's why it takes 24 to 48 hours. But that's why they build a simulator, an emulator of the hardware, such that you can check the correctness of your program without the hardware. And that's what we did since for the whole development, and we are still sitting there. Okay, let's have an example. So, yes. So, CGPOT, it's our results that we want, okay? That's an array, okay, and then we set it to 0. Then we go through our modes, the modes of our system. So that's a 3D system, so we have three 3D modes. Then we have a quantity that we will have a reduction. So that's pretty complex. So that's not the hello world, okay? But the thing is that it's complex enough such that you can see the problem with FPGA programming because you have reduction. reduction is the problem with FPGA. So you have this quantity that will be our reduction, then you compute something that depends on the mode you are considering. And for each mode, then you have to go through all your atoms. So n melt is the number of atoms you have in the bulk, okay? And walls is the number of atoms you have in the electrodes. And for this, you have to sum up, so an operation that makes something that depends on the atom you are considering with the mode you are considering. Once you have this quantity, then you can compute the quantity of interest that applies only on the atom of the electrodes, and then you multiply again with the same quantity before. Okay? How do we implement this in an FPGA? Yes, first. First, our players, so that's our data. Okay, we will have 3 modes in total. So in our example, because I made an animation, but so that's just a toy animation. Of course, you have much more atoms and modes in reality. We will have walls with 3 atoms and 9 atoms in the melt. Okay, and that's so each color is a different atom. Okay. Okay, that's how it looks like on an FPGA. You will have our mode that will be generated from the silicon with simple counters. Okay, LMN will be generated. Then you will sum in order to have L plus M plus N here, make the cosine here. And then the K will flow, so that will be one kernel. Then you will enter a second kernel that will make the multiplication between K and the D that will depend on the atoms. Okay? And then you will make the reduction, so the results of the multiplication, you will add it with the current value of the reduction operation until the end of this kernel, and then the result will flow into the third kernel, and so on. So the whole game in FPGA programming is to build such kind of long pipeline as long as possible and trying to make all the kernel busy at the same time, concurrently. Let's see how it looks. Oh, yes, and then before going on, and you know exactly how many ticks you will need in each kernel. Here, this kernel will have NB modes, ticks, okay? You not need one, not less than one, not -1, not +1, but exactly the number of modes. Ticks, here you will have number of modes times the total number of atoms. And here, the number of modes times the number of only on the number of atoms in the electrodes, as only CG pot is as the size of is applied only on the electrodes. Okay, let's animate. Okay, that's our first value of LMN. I can do so. Next tick, first addition is done. Then you can start generating the next one. And then you go on. Then here I have L plus M plus N for the first value. And then you generate the third one. Okay. Then I can do the cosine here while the other are still flying in. Okay. And for now, this kernel is idling. Okay. Is waiting for inputs. Okay. So I have my first K that comes, and then I can this one then can start. Okay. So then here I pull data from memory. I have my first atom from the melt that is here. I'm ready to make the first product, and this one is almost ending because I have only 3 modes here. So the third value will go out, and then we will be done with the first kernel. First kernel now is idling. And then we can go on initially we had 0, so then the result will just go there. And then we go on with all the atoms of the melt here. So here we have only one kernel running. Okay? So now that was all the melt, now the walls are starting to come in. Good. So, and then, yeah, something important. So that's the last atom of the wall with this first value of k. Okay. So now I can switch to the second value of k with, again, the first atom of the melt. While our first variable on the reduction variable is not finished. Okay, that's the last point for having our reduction. Okay, and then I have my value that can flow to the third kernel. Right? Then I go on. Now I can activate the third kernel. While now we have then two kernels that are active concurrently here. Okay, so that's the whole game. If you can make all the kernels busy at the same time, then you have a chance to reach peak performance of the chip. That's how you play with. All right. Yes, and so on. All K are used. And now, that's the beauty of FPGA. Now I can build a dedicated vector unit for my algorithm, not for an operation. Here I have, that's the same kernel as before, but replicated 3 times on the silicon. Okay. Now instead of having one atom treated 1 by 1, I will treat them 3 by 3. Okay? And that's the same picture. So now doing the first, and then instead of having 9 iterations, I only need 3. Okay? Then I have my, that's my last iteration. And then I have my first value here. Okay? And then I can start with then the last one is fired up. And then now I'm 3 times faster with the last kernel, and then that goes on until the end. This time, okay, that's my last value. Okay, here and then that's the results of my algorithm. So that's the first value. So and I need 3, okay, and then I need 3 more ticks to output the value back to memory. Okay, that's the whole idea, and it's quite funny. At least I find it funny. Right, so I'm almost done. So what's the status with Metalwalls? So for now, we spent, in terms of development time, as much time as GPUs to reach this status for FPGA and learning FPGA from scratch, okay? We have kernels implemented in unit tests, so inside this Eclipse stuff. We have a proxy application that is calling these kernels. That works, all in the simulator, okay? In the simulator, not hardware. We never made a first compile yet, so because we need the hardware and the compiler and everything, so that's a bit complicated, but hopefully before summer I will have this. And our performance model tells us that running on one single FPGA is between 3 and 5 times faster than a Haswell node. Okay, for almost 10 times less energy. Okay, so I would say that's promising. So that's what our performance model is telling. I'm really eager now to test it for real and to measure and to see how what comes out. Right, so I'm at the conclusion. So now we have, so thanks to the work in ECHO, we have MPI plus OpenMP and MPI plus OpenACC implementation of Metalwalls. Performance has been improved by a factor of 3.5 compared to the initial version, so that's quite nice, I would say. When we are running this new version at scalability limit, so Broadwell architecture is still the fastest. KNL and GPU are a bit behind, but not that much. And from the energy point of view, GPU is clearly the best, KNL being more than factor of 2 behind. Okay. What is important, at least for the physicists, is that we manage to keep only a single code base. We don't have very complicated software to maintain, so it's, I think, reasonable, the kind of shape. And yes, and doing the porting work to GPU and KNL brought us some insight on, and then it's faster also on CPU. Okay. So that's a huge work. So to make specific porting on GPU and working on optimization for KNL is a lot of work. Okay, so it brings something on CPU back on CPU, but if you do this only for the thing that you are back on CPU, that's very time consuming. And again, Metalwalls is a very small code, so that we are here that's easier also for us for this reason. Future work, but to make my first plots on results more complete. So it's about energy measurement on Broadwell and Skylake, and test and energy measurement on Maxeler, typically to have these numbers and to have my point, to add a blue point there. Yes, and the last one is Abel was fed up with the code base and started Metalwalls from scratch again. So. And yeah, now, so this guy is brilliant. So he starts from scratch, and so 4 months later, now we have a new version, and it's working. But yes, we have to do again the OpenACC and OpenMP implementation, and maybe the FPGA. So we will see what comes out. But okay, we might have to start from scratch. Okay, thanks a lot for your attention.